Imagine you are a detective trying to solve a mystery. You walk into a room and you see clues: broken glass, muddy footprints, and an open door. Your job is to figure out the most likely story that explains these clues. Was it a break in, or did the cat knock something over, or anything else? The process of trying to figure out a story based on clues that you observe is pretty much how maximum likelihood estimation works. Given the data we observe, we try to find the most likely parameters that explain this data. If you can be with me for the next few minutes and focus, I promise that you will walk away with a crystal clear intuition of what maximum likelihood estimation is and how it works. Let's break it down. It's like having clues. So say clue 1, clue 2, and then examining these clues, trying to come up with a story. Now, maximum likelihood estimation is finding the most likely parameters given observed data. So you can think of these clues as data, and the story is a model with some parameters that you estimate. Let's now explain the concept of likelihood. Imagine you have a biased coin and you don't know what's the probability of heads, and we want to figure out what that would be. Now, if it wasn't a biased coin, then you would expect that the probability of heads would be 0.5. However, because it's a biased coin, so we need to figure this out. And I want to give this as an example to explain what likelihood is. So, we have the unknown, which is P, probability of heads. And then to figure this out, what we do is that we flip this coin a number of times and then we observe that data, for example, to see how many times did we get heads. So observed data, that would be, so let's assume we get k heads in n flips. So likelihood is the probability of observing these k heads for a given value of p. So the likelihood function that we can write as L of p, that is equal to probability of the data for a given value of p. So that's what likelihood is. Let's use an example of something other than coin to explain this concept. Imagine two friends arguing which sport is popular, and one loves cricket, the other loves football, and they want to figure out which sport is the most popular in their country. Now, one way to settle this would be to ask everyone in the country, but that's not feasible. So what you do instead is that you can ask a subset of people to find out whether they like football or cricket. So imagine they go out and they ask 10 people, and 7 say that they love football and 3 says that they love cricket. You could use this to say that, okay, maybe football is more popular. However, what if there was some kind of a bias when you were getting this data? For example, if you go to a football stadium and ask this question, so there's a very high chance that everybody will say they love football. Or maybe the sample size is too small, and if we ask another group of 10 people, maybe the answer would be completely different. This is where maximum likelihood estimation comes in, because it gives us a principled way of approaching problems of this kind. Let's assume that in the total population, football fan proportion is T. Then cricket fans would be 1 minus T. And we need to find so say we ask 10 people, so n equals 10, and then 7 people say that they love football. which means 3 loved cricket. Now imagine that this sequence that we get goes something like this. So the first person says football, the second says football, 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 and then we have cricket, then football, football, cricket, 3, 4, 5, 6, 7, 8, 9, and then okay. So that's the sequence that we get. Now the probability of observing exactly this sequence, let's call this sequence. So the probability of observing this sequence would be p power 7 multiplied by 1 minus p raised to 3. Hopefully this should be very clear. This is because each person that you ask is independent. So the probability of somebody saying that they love football would be p, and then the probability of anyone saying that they love cricket would be 1 minus p. And because all these, the questions that you ask for each person, they're considered independent, so all you do is to multiply either p or 1 minus p. And you have 7p, and 3 times is 1 minus p. So in the end, that's the probability of observing this particular sequence. But here's the thing. There are many possible sequences where 7 people choose football and 3 choose cricket. For example, instead of this sequence, we can also have maybe the first 2 people like cricket, and then we have football, 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 cricket, right? And then you can have other sequences, maybe the first 3 like football, cricket, and then the rest like football, 3, 4, 5, 6, 7, and so on. Now, how many possible sequences are present when we are working on this? And this is where binomial coefficient comes in, because effectively what binomial coefficient does is that it's so if you think about it, it's effectively a question of how many possible ways are there to arrange these 10 items, where 7 are of one type and 3 are of different type. And the way we write this, so the number of arrangements that are possible, we write this as a binomial coefficient. So n choose k, which is equal to n factorial divided by n minus k factorial and k factorial. Now in our case, n is 10, k is 7. So when plugging these numbers, what we get is so the 10 factorial divided by 7 factorial multiplied by the denominator 3 factorial. So this will be equal to 10 multiplied by 8 multiplied by 7 factorial divided by 7 factorial minus 3 multiplied by 2, 6 So this will cancel with this. 3, this will be 3, this will be 4, and then it's 4 times 3, 12, 12 times 6, 100 and 120. So the likelihood function is, so if L of a particular sequence that we had, the probability of that is p times 7 multiplied by 1 minus p times 3, okay? And we can have observing 7 football fans and 3 cricket fans. That would be equal to 120. So there are 120 possible ways, and this would be a simple summation of all of those individual sequences. 120 times p times 7 multiplied by 1 minus p times. So this is the likelihood function that we get. Now to find the value of p that maximizes the likelihood, we could just, all we do is, so this is now a simple function. So we could plot this function, and then find the p which maximizes p, and that will be maximum likelihood. So what do I mean by this? So we have this L of p. All I could do is, so imagine if I plot this, maybe I'll get something like this. I have p, and this is L of p. I'll get something like this, and if this is the maximum L of p, whatever the value is, so then this p. So then what we mean here is that this is the most likely value of p if we observe the data that we actually ended up observing. So I use Python to plot this, and actually, if I do this, this is what I get. This is L of p equals 120, and then the maximum that I get is here, which is actually 0.7, and that's the maximum likelihood estimation. So conceptually, once you figure out what the likelihood function is, all you do is you can plot it and then find out what's the maximum value of the parameter which maximizes that function. However, in reality, we wouldn't need to plot this, because what we do is we use calculus. We take the derivative of the likelihood function, and then that will give us the maximum value. Rather than maximizing the likelihood function, what we do is we maximize the log of the likelihood function. Now, why do we apply log? I'll come to that in a bit, but let's just quickly do it for the equation we already have. So, 120, 7, 1 minus 3. So, if we take the log, this will be log of, and that will be
And then if you differentiate the log of L with respect to P, so that's the answer because the constant goes, and we get from this, that will be 7 by P, and that's minus 3 over 1 minus P. We set 0, and we solve this, we get 7 by P equals 3 over 1 minus P. So, we are defining the maximum value estimate of P simply proportion of H and beta. That ends up being 7 by 10 equals 1.
Now let's talk about why do we take the logarithm. So, multiple reasons. Now the first is that it helps us convert product into sums. It simplifies the math, and the likelihood function, most often it will contain lots of product terms. The simple reason for why it contains lots of product terms, if you think about it, think of a likelihood function, which is the probability of the data that you observe for a given parameter. Now, when you have data, typically you will have multiple data points, and we assume that those data points that you get, when they are generated from a given probability distribution, those data points are independent. When you have multiple data points and you write their joint probability, it will be a product of the probability of each individual data point. So in the end, the likelihood function will have lots of product terms. So rather than dealing with that likelihood function, which will have lots of product terms, what we do is instead we apply the log, and then those product terms gets converted into summation. The other reason is that this conversion also makes it more stable. Probabilities are going to be between 0 and 1, so they'll often be small numbers, and when you have multiple small numbers and you multiply them, they end up being really small, and that is also not ideal. Imagine if you have lots of these small numbers. And the key point is that the location of the maximum does not change. Whether you try to find the value of the parameter for which the likelihood is the maximum, or if you want to find the parameter for which the log likelihood is the maximum, in both cases, the value of the parameter would be the same. So there's a simple code that I have written to explain. If I take the likelihood function, if I plot the likelihood of what we have, so for the same value, so I import the required libraries, then the total trials, what we observe, so the range of the parameter values. So I have the likelihood function, and then I also take the log likelihood. Now what I'll do is, and then I'll plot both the likelihood and the log likelihood. Now once some minor things that I've done, so I've done some normalization to make sure that we can compare them visually in the same plot. So when we run this, this is what we get. Now if you notice, so the dotted line is the log likelihood and the blue is the likelihood. And what you see is the shape has changed. However, the location of P for which we get this maximum, that stays the same. So to conclude, maximum likelihood estimation is a powerful tool for uncovering the most plausible explanations behind the data that we observe. Maximum likelihood estimation provides us with a principled framework to estimate the parameters that make our observations most likely. Let me quickly recap. So we observe some data, then we create a likelihood function which is equivalent to saying that probability of data given a certain value of a parameter. That's the likelihood function. Once we do this, we then convert that into log likelihood for mathematical convenience, and then we use calculus to find the maximum value, and that's your maximum likelihood estimation. Thank you for listening. Let me know in the comments if there are specific topics you would like me to explain, and I'll see you in the next video.